All right, welcome back. We're going to be learning about mass transfer in lesson 4 and the role that it plays in electrochemical reactions. In the overview, we introduced the concepts of diffusion, migration, and convection. Just as a reminder, we'll briefly review them here. Diffusion is the movement of a species as a result of a concentration gradient. Migration is the movement of a charged body under an electric field. And convection is the movement of species due to bulk fluid flow from natural, like thermal or density gradients, or forced, like stirring or pumping convection. It's color-coded here. You can see how it works out mathematically. This blue is our diffusion term in the nernst-plank equation, where we can see the concentration gradient by a derivative of the concentration with respect to distance. And we can see that migration is in green, and that's this Z here represents the charge of a particle and how it responds to potential gradients in the cell. And then the C times this velocity term in red represents our convection. So if you're more of a visual learner, this graphical representation should help you get a concept of this. So as we are having an electrochemical reaction at an electrode, we have the species being consumed. If this was reduction, we'd have an oxidized species being consumed at the surface of the electrode. And so we'd have some lower concentration at the electrode rising up, going out to the bulk of the solution away from the electrode. So diffusion typically occurs only near electrodes. Migration is the response of charged particles to an electric field. And so we can see here that this sodium cation migrates towards the cathode, which has a negative charge. And then the chlorine anion migrates towards the anode, which has a relative positive charge. So migration occurs both in the bulk and near electrodes. And migration is what's responsible for carrying the charge or the current through the bulk of the electrolyte. Convection occurs in bulk solutions. And then typically once we get closer to the electrode, you get a small stagnant layer that is diffused through. And so here in this example, we have an electrode that's being rotated, which creates these velocity profiles or currents that flow up towards the electrode and then out. So the forces that drive mass transfer arise from gradients in the electrochemical potential and imbalances in the mechanical forces. So in lesson 2 on potentials, we introduced the concept of electrochemical potential. Diffusion and migration both arise from this gradient and electrochemical potential. So here we have the flux represented by this big J of species little j, and that's going to be equal to some proportionality term times by the derivative of our electrochemical potential with change in location. So that's the one-dimensional representation. On the right here, we have the three-dimensional gradient of our electrochemical potential. So convection is represented by this second term below here, added to our electrochemical potential gradient. We have the concentration times the velocity in 1 dimensions, and then at the bottom here, we have it in 3 dimensions with the gradient of our electrochemical potential plus the concentration times by velocity vector. So how do the migration and diffusion terms arise from this electrochemical potential gradient? Well, we'll show the derivation here in 1 dimension. So here we can see we have our derivative with respect to x of the electrochemical potential. From lesson 2, the electrochemical potential was defined as this term here in the brackets. And so the derivative of our standard electrochemical potential will be 0 because that's a constant with respect to our change in location. And then the derivative of our RT natural log of our activity coefficient and our standard potential will be given by, will be 1 over the concentration of our species. And we are going to assume that our activity coefficient is relatively constant in a mixture. If you have major changes in concentration going from the electrode to the bulk or the bulk to the electrode, we will need to revisit that assumption and possibly capture the activity effects. But for now, we're just going to assume that we can simplify this by saying that our gamma j of x is relatively constant. So that doesn't change with position, and so we don't need to take the derivative with respect to position on that one. And so the derivative of the natural log of our concentration with respect to x will be 1 over that concentration of function of x times by the derivative of that function with respect to x. And then our local or electrostatic potential, we'll have to take the derivative of that with respect to x as well, because that changes with position in our mixture. And so we can see here that we're getting close to what we saw on our initial slide of the nernst-plank equation. We need to recognize here that our K, this K that we've been using to relate these to the flux, will need to be the diffusion coefficient of the species J times the concentration of the species J divided by our universal gas constant and temperature. If we plug that in, we arrive at the nernst-plank equation. Here we have the one-dimensional and the three-dimensional nernst-plank equation. So we can see how electrochemical potential is the root of where our mass transfer arises from for diffusion and migration. So how do we relate this to current? Well, depending upon the charge of our species and how we have oriented our space domain, we will need to take plus or minus the charge, which is represented by the Z of the species, times by F, and A, which is the area of our electrodes, times by the flux of our species J. And that'll be the current of species J. You may see in some textbooks that they have a negative sign in front because of the convention they're using, which they may be taking the reduction current as being positive. And however, in these slides, we are using the UPAC convention, where the reduction current is negative. And so we've got to think about how we set up our system here. So if I take the cathode as position 0 at the surface of the cathode, then as I move from left to right, I will have a positive gradient. So my change in concentration with respect to x is increasing as I increase in x. Similarly, I could have a similar type of profile as we have here in red for my electrostatic potential. And in that case, I would have a positive gradient as well. And that makes sense because here our anode is positive, our cathode is negative. So we're moving from a higher potential, electrostatic potential, down to a lower electrostatic potential. So if I have a positively charged ion, I'm going to need to just leave this alone so that I have this negative D gradient of my concentration, which will be positive. So then I end up with a negative value for my current. The main thing you got to check when you convert from your mass flux to the current is, am I in the convention I want to be? And if you're in the IUPAC convention, then if you're experiencing reduction, you should have a negative current. Okay, so we can imagine the current being split up into 3 components. We have the diffusive component represented by this D, the migration component, and the convection component. The convection component will not be addressed in this lesson. It will be addressed in a later lesson when we cover rotating electrodes. The current species J will then be equal to this equation here. And because we're neglecting convection, we're assuming a stagnant solution, we've dropped the convection term here at the end. So if I want to know the total current, I'm going to have to sum up the current of all of species J for each species, and then I can pull out of each summation sign here anything that's not directly species dependent, and I get this equation here at the bottom to relate the total current to each individual species. So convection, we're punting to a later lesson. Migration we'll cover right now in this lesson. So the migration component, if we're in the bulk solution, the current is solely carried by migration. And so we can represent the current of the species solely by this portion of the nernst-plank equation that we've seen before. And so for convenience, we're going to define this ionic mobility, which consists of the diffusion coefficient of species J times the absolute value of species J times Faraday's constant over the gas constant times the temperature. We can also define this equivalent ionic conductivity, which gives us an idea of how much ionic conductance a certain ion has. And that's going to be Faraday's constant times by this U that we just defined. And so we'll use that to more conveniently represent transference here below. So transference of a species is essentially how much of the current is being carried by migration in the bulk solution. So the current of species J over the total current is the definition of my transference. And that's going to be equal to the absolute value of my charge times my Faraday's constants times by the area of my electrode times the mobility of my species J, the concentration of species J, and the potential gradient. In the denominator, I've pulled out all of the non-species specific things, and then we have a summation term summing up all of the species in the solution so that we get the total current. So these non-species specific things will cancel out. Faraday's constant, our area, our potential profile. And so then we're left with just the charge, mobility, and the concentration. We can likewise represent this in terms of equivalent ionic conductivities, which may be more convenient at times. So let's get an idea of how this works. How does migration work in a cell? Well, we're going to do a simple model. It may not be 100% accurate to what takes place, but it will give you an idea of how to wrap your head around how diffusion and migration play a role and interact with one another. So we have this power supply that's driving about 10 electrons per some arbitrary unit of time. And so those 10 electrons need to transfer to 10 or an equivalent charge of 10 positive charges being carried by cations in the solution. And so we have a cathode where we have the negative charge where electrons are flowing into, and then we have an anode with a positive charge where electrons are flowing out of. And so because we have this potential gradient between the anode and cathode, we have hydrogen ions migrating towards the cathode. We have chlorine ions migrating towards the anode. Well, how can we get an idea of how much is migrating? So we got to use this equivalent ionic conductivities. So for hydrogen, that's 350 centimeters squared per ohm. For the chlorine anion, it's 75 centimeters per. And so we've got these two reactions occurring. Well, the hydrogen ions are going to hydrogen gas. The chlorine gas is forming two chlorine anions, or if we're oxidizing, we're going the other way, where two chlorine anions are being oxidized to chlorine. So to get an idea of how much of the current is being carried by each one of these ions, we're going to calculate the transference. So the absolute value of the charge of hydrogen and chlorine are the same. So we can pull this guy out of the summation term because they're both 1 and cancel it out. The concentration of the hydrogen and chlorine is the same since we're using HCl to put these ions in solution. So we can pull this guy out as well and cancel it out with the concentration. So we're just essentially taking lambda H plus over lambda H plus lambda chlorine minus. For the chlorine minus, our numerator just becomes the lambda for the chlorine minus. So this roughly works out to be, for the transference, we have about 80% of the current being carried by the migration of hydrogen in the bulk, and we have 20% of the current being carried by chlorine. So we have 8 hydrogens in the bulk solution here migrating towards the cathode, and we have 2 chlorines anions migrating towards the anode. So because the anions flowing in the same direction as the electrodes, we're going to make that as the electrons, we're going to make that a -2. And then we have 8 positive charges moving in the opposite direction, which is equivalent to 8 negative charges moving in the same direction as the electrons. So that works out to a -10 charge being moved across the bulk of the electrolyte. And so we should have that same equivalent amount of charge moving through our diffusion layers. And so in order for 10 electrons to be flowing, these 8 hydrogen ions that make it to the cathode via migration will be reduced to hydrogen gas. But we need 2 more electrons to be exchanged in order for these 10 electrons to flow. So 2 hydrogen ions are going to be brought to the cathode using diffusion. And because that's associated with the chlorine anions, 2 chlorine anions come with. And so in this diffusion layer here next to the cathode, we have 8 positive charges moving towards the electrode to the left, which is equivalent to 8 negative charges. So here we have a minus sign out in front. And then we have the positive 8. But we also have two more positive charges moving towards the cathode via diffusion. So here we have a +2. And then we have two chlorine anions moving towards the cathode as well. So here we have -2. And once we distribute that negative through, we will have here in the bottom, we'll have 8 + 2 -2, so it's still 8. And then we still have these two chlorine anions migrating towards the cathode, even in this diffusion range here. So we still have this -2 up top. And so we end up with still a -10, an equivalent of 10 electrons or 10 negative charges moving in the direction that we need it to from left to right. And so the same thing is occurring over here in the diffusion layer, slightly different though, because we only have two chlorine anions moving via diffusion to be oxidized to chlorine gas. So at the anode, we need 8 hydrogen ions diffusing towards the surface and 8 chlorine anions diffusing towards the surface. The hydrogen comes along with the chlorine because once again, they're associated. And so then that brings enough chlorine anions to the surface to be oxidized to chlorine. And so this should be a 4 here. And so we have still our 8 hydrogen ions migrating towards the cathode or towards the left, which is equivalent to a -8 charges moving towards the anode. And so then we have still our 2 chlorines migrating towards the anode, but we also have this additional 8 diffusing towards the anode in this diffusion layer. Plus we have our 8 positive charges, that should be positive. And so these cancel out, 8 - 8, and then we still have our equivalent of 10 negative charges moving in the direction that we need it towards the anode so that we can complete the circuit and flow 10 electrons back to the power. So that's a very simple example how you can see how diffusion and migration work in tandem to bring the needed ions to the electrode surface so that the electron exchange can occur at the rate needed. So now it's your turn to pause the video and try to fill in the blanks here and see if you can calculate the transference. Start by trying to calculate the transference and then calculate the number of electrons exchanged. And then it's easiest then to go to the bulk and calculate how much is migrating of each ion. And so in this case, we have 1 molar of NaCl added to our HCl mixture of 0.015 molar. And so we still have the same reactions occurring of hydrogen evolving at the cathode, chlorine gas evolving at the anode. The additional piece of information you need to solve this is that the ionic conductivity of our sodium ions is 50 centimeters squared per, and if you recall from the previous slide, our lambda H plus was equal to 350 in the same units, and our lambda chlorine minus is equal to 75 in the same units. And one last thing you need to know before you fill in the blanks is that our chlorine, our concentration of hydrogen is not equal to a concentration of chlorine because we have additional chlorines being added by our sodium chloride. However, the charges are still the same, but the concentrations are not going to be equal. So these concentrations will be different for each one. So pause the video here and see if you can fill in the blanks. Okay, welcome back. So to calculate the transference here, we're going to need to take our charges, will all cancel out because they're all 1. So we can take this guy out, factor out all the absolute values of z since they're all the same, and cancel out with the 1 up above. And so we're going to have to take the lambda times the concentration for each species to calculate this out. So I'll show it here for hydrogen, and I'll just fill in the rest so you can check the answers for the chlorine and sodium ion. So here I'm going to have my 350 centimeters squared per ohm times by my 0.015 molar for the concentration of my hydrogen ions all over my 350 centimeters squared per 0.015 molar. I'm going to start leaving off because everything's going to have the same units top and bottom. I'm going to start leaving these off to make room so it's not all crammed in here. So it's going to be 350 times our 0.015 plus our 75. Now the concentration of chlorine will be this 1 molar plus the 0.015 molar. So that's 1.015 plus the 50 sodium ions times 1. So if you plug this all into a calculator, again, we're dropping the units since they're all going to be the same top and bottom. Cancel out. So if we plug this into a calculator, this approximately works out to be 0.04. My chlorine works out to be 0.58, and my sodium works out to be 0.38. So all these transferences should add up to 1, since it represents the fraction of the current being carried in the bulk of the solution by each species. So if I add this up, I get 8 plus 8 is 16 plus 4 will be 20. So that'll be 0. Carry my 2, I'll have 2. Plus 3 will be 5, plus 5 will be 0. Carry my 1, and sure enough, I get 1 when I add those up. So that's a good check. So now the next easiest place to start is to look at the bulk. We have 100 electrons flowing per some arbitrary unit of time. I'm going to have 4 hydrogen ions migrating towards the cathode. I'm going to have 38 sodium cations migrating towards the cathode. And I'm going to have 58 chlorine anions migrating towards the anode. So in the bulk, I will have negative 58, since I have a negative charge flowing to the right. And then I'm going to have this 4 plus 38, which is 42. Since it's flowing in the opposite direction to the left, it's as if we're moving 42 negative charges to the right. So I'll take the 58 minus the 42. The negative 58 minus 42 is minus 100. So that's great, but these 4 hydrogen ions are only providing 4 electrons to be exchanged. So that we need to come up with 96 more electrons. That will be provided by the diffusion of 96 hydrogen ions. The sodium cations cannot be reduced in an aqueous solution. It's outside of their electrochemical stability window. Since the hydrogens associated with chlorine anions, we have to have 96 of them coming along. And so now we have negative 58 anions migrating towards the anode. So they're moving to the right. So that's a negative 58. And I've got minus 4 of my hydrogen cations migrating to the left. And I've got my 38 sodium cations migrating to the left. So they're going to be all times by this negative, because they're going in the opposite direction as the negative charges. And then we've got plus our 96 hydrogen cations moving to the left, opposite of the movement of the negative charge. And then we've also got negative 96 anions moving to the left. And so this will be this negative. This will be also times by this negative because it's moving to the left away from the anode. And so these 96 cancel out, but I have this negative 58 minus my 42 of 100. So over at this other diffusion layer, though, we will have 58 chlorine anions being brought to the anode with migration. And so we're going to have 58, not 2, 58 electrons being exchanged, which will result in 29 chlorine molecules being formed. So that means we still need 42 electrons being exchanged here, not 8. And so that means we're going to need 42 chlorine anions diffusing towards the anode, which will bring 42 hydrogen cations with it. And so we're going to have our minus 58 chlorine anions from migration moving to the right in the direction of where we want our electrons to flow. Then we have our minus 42 chlorine anions diffusing in that direction that we want our electrons to flow. And then we've got our 4 positive charges moving from migrating towards the cathode, the opposite direction, plus our 38 sodium cations, positive moving in the opposite direction. But we have minus 42 hydrogen cations moving to the right. So that cancels out the movement of our negative 42 chlorine charges. So then we're left with our 58 minus our 42 again, and we have minus 100. So we can notice here that basically 96% of our hydrogen ions are being brought to the cathode via diffusion. And so we could assume here that only diffusion is occurring and we'd only introduce a 4% error in our flux. And so that introduces a powerful concept that we can add certain ions to our solution to reduce the impact of migration on our electrochemically active species. So on the right here, we didn't have that same effect with chlorine, but we could get that same effect with chlorine if we had added something like sodium nitrate, so where we could have introduced a lot of a different anion. A quick note here before we move on. It may seem here as if we're getting an accumulation of negative charges here and an accumulation of our positive charges here at the anode. But for example, here we do have 96 chlorine anions diffusing towards the surface, but we also have 58 chlorine anions migrating away. Our positive charges are being removed here to make our 48 hydrogen bubbles. And so we will have some buildup of chlorine anions, but that will then be compensated for as we get a concentration gradient, and that'll increase the diffusion away from the cathode. So not the perfect representation, but it does give you an idea of the interplay of diffusion and migration in the cell. So going back to this point that you can have 96% of your flux of an ion simply due to diffusion by adding a supporting electrolyte, which is quite helpful. The supporting electrolyte typically has a high solubility, so like sodium chloride and water, we can dissolve a lot of it in there. It carries almost all the migration current. So as we saw in the previous slide, our sodium and our chlorine ions are carrying most of the current. The hydrogen ions are only carrying 4% of the migration current in the bulk. And so that means when we get to the surface of the electrode, the electroactive species, which is our hydrogen in the previous slide, occurs almost exclusively by diffusion. So we can make that assumption and simplify our math. The other important thing about the supporting electrolyte is that it's electrochemically inactive at the electrode surface. So like the sodium cation couldn't be reduced. So therefore we had to use diffusion to bring the 96 other hydrogen cations. And so you'll want to use something that's inert enough that you have some window where you can interrogate your species of interest. So for example, if this is my current versus potential curve, and if this is the limit of my species, and here's my limit as well, I want to add species that won't react near where I have my electroactive species. So let's say my electroactive species will start to react here. I'll want to make sure that my supporting electrolyte is either not reacting too close to the boundary of our electrochemical window, or it's outside of our electrochemical window, ideally. So these can be chlorides and water or nitrates, all sorts of salts are great. And typically the alkaline or alkaline earth salts are quite useful at being supporting electrolytes. So some advantages and disadvantages of supporting electrolytes is that the advantages is that they decrease ohmic resistance. So the more salt I add, the better the conductivity of my electrolyte. It also simplifies our cell design and our analysis. As mentioned, we can make assumptions like only diffusion is occurring for our electrochemically active species, and it reduces double layer thickness. Some disadvantages are because we have to add such an excess of it. Typically, you want to have at least 100-to-1 ratio between your supporting electrolyte and your analyte. And so impurities in your supporting electrolyte, even if they're a small amount, can play a significant role, especially if they're electrochemically active, like they're absorbing or desorbing, or they're reducing or oxidizing. And so that's something to watch out for. The other thing is that the supporting electrolyte can alter the properties of the medium. And so if you're really interested in understanding, say, the diffusion of these hydrogen ions in pure water, but then you add a bunch of sodium chloride, well, that's going to alter the behavior of your fluid, the viscosity, or some other property, which will then impact your diffusion measurements. And so you may have to look for a different way if you're really interested in seeing it inside the pure water. Okay, some quick notes on diffusion. Diffusion is going to be used a lot as we start looking into the derivation of a lot of these electrochemical techniques like cyclic voltammetry. And so let's get a little bit of understanding about that. So diffusion occurs near the electrode surface. And so if we're near the electrode surface and we have a supporting electrolyte, we can assume that all of the current is due to diffusion if we're just reacting dilute analyte. And so we can make this statement here that our current is equal to the negative charge of our species times the Faraday constant times the area times the diffusion coefficient of the species times the concentration gradient. So each molecule will travel no distance or some fixed distance, and we'll get some distribution. But the diffusion coefficient basically takes that average path or distance traveled, squares it, and divides it by 2 times the amount of time lapsed. So diffusion coefficients are typically reported in electrochemistry as centimeters squared per second. You'll also see it as meters squared per second. So it typically has length squared per unit time. The Stokes-Einstein's equation is actually surprisingly accurate, and it calculates the diffusion coefficient of a species by using the Boltzmann constant times the temperature over 6 pi times the viscosity times the radius of the species J, the atomic or molecular radius, or the radius of the diffusing particle. So if it's complex, we need to get an idea of what is the size of that complex that's diffusing. And so as we increase in temperature, our diffusion coefficient will increase, although the most significant increase due to temperature is the change in viscosity, which has an Arrhenius relationship with temperature. As we increase in temperature, we exponentially decrease our viscosity, making it easier for particles to diffuse through the solution. As we increase the radius of our diffusing particle, it decreases the diffusion coefficient. So the Stokes-Einstein equation gives us some intuition of what to expect with the diffusion coefficient as we alter these variables. So the flux, when it's diffusion controlled, is dictated by Fick's first law, which we have seen in the nernst-plank equation. The second law gives us the concentration distribution, or how the concentration changes with time. And that's just the second derivative of our concentration with respect to space times our diffusion coefficient. And so here we see both of these given as one-dimensional and three-dimensional terms. Here they're given in this slide in our planar or linear coordinates. However, we will be working with cylindrical electrodes, so we may be using this Laplace operator, and then we will be giving it in spherical, and so we will be possibly using that. So those are the different types of electrodes and coordinate space that you'll need to work with it. To solve these differential equations, we need some boundary and initial conditions. Some common boundary conditions are the semi-infinite boundary condition, that is, as we get infinitely far away from the electrode, our concentration approaches the bulk concentration of the species, which we can easily measure and know. At the electrode surface, if it is a rapid reaction, we can apply the Nernst equation to get the ratio of the concentrations of the oxidized and reduced species based on the potential applied or measured at the electrode. Then we also know that at the electrode surface, our flux of our oxidized species will be equal to an opposite of the flux of our reduced species. And the initial condition commonly used is that we assume that at time 0, before we start applying any potential or current, we have a uniform concentration in our solution. So at everywhere at time 0, where you have our bulk concentrations. So using Fick's law, we can get an idea of what our mass transfer limited current would be. So that's like the fastest we can go, which means we're going to have the steepest gradient, which means our concentration is going to go to 0 here. And then we're going to have this steep gradient rising up to our bulk concentration. We can approximate this as linear, and so that's represented by this line here. And where this intersects, this is what we'll call our diffusion layer thickness. And so we have this mass transfer coefficients out in front here. And this simply arises from this approximation that our change in concentration is linear and our distance traveled is linear. So we have these delta concentrations and delta distance. And if I group my diffusion coefficient and my delta x together, then I get my mass transfer coefficient, which our delta represents our change in distance over the diffusion layer thickness. And so we have our steepest and strongest gradient when our concentration at the surface is 0 of each of these. So this will represent our limiting cathodic current and our limiting anodic current that we can experience at either the anode and cathode.